Hello, I'm Brendan Marks, CEO of Capture H2O. Thank you for your interest in our training series on cooling water treatment and cooling water savings. Today we're going to cover everything from cooling water and cooling tower basics all the way through wireless monitoring, how to do tests, and much, much more. We appreciate your interest and your time. We hope you find this valuable. Thanks.
Hi, my name's Anthony Rowan, lead engineer at Capture H2O, and we're going to be talking about cooling tower systems. So what you see on the slide here is a cooling tower. A cooling tower was invented really to solve two challenges. First, to remove heat from one location and dissipate it to another. And the second is actually to conserve water. So this is a cooling tower unit. You may see this on top of an office building or tucked around the corner at a manufacturing facility. They're typically not front and center at these facilities and buildings. But they serve a very important purpose to provide comfort cooling for HVAC or process cooling for pieces of equipment. As you'll see on this next slide here is a cut view of a cooling tower system. On the left side is the cooling tower unit itself. It has cold water, which is represented as blue in this diagram, sitting in the basin of the cooling tower. What happens next is we pump some of that cold water to some process that needs to be cooled. Whether that's a chiller or a heat exchanger or some other system, we're picking up heat from that system and transferring it to the cooling tower loop, which is represented by the red on this figure. As we pump that cold water to the process and the hot water is leaving that process, returning back to the cooling tower, what happens next is where we get into the water savings function. You could theoretically take all of that hot water and send it directly to the drain, or you could send it back to a cooling tower. And the cooling tower will accept that hot water at the top of the unit, and the large fan we saw on top of the tower on that last slide is pulling in cool air into that cooling tower. As that hot water falls down the cooling tower and that cool air is swept up into the cooling tower, that cool air interacting with hot water will induce evaporation of some of that water, which will then leave through the top of the cooling tower. As evaporation occurs, the phase change from a liquid to a vapor will consume some energy and allow that remaining water that reaches the bottom of the cooling tower to be cooled and available for reuse. So instead of taking that water and sending it to the drain, we're sending it back to the cooling tower, evaporating a portion of it, and being able to reuse the remaining water. Now this process continues and continues as the tower operates, evaporating just that pure water, just that pure H2O. All the minerals we can't see with our eyes, the dissolved solids in the water, such as magnesium, calcium, and silica, are concentrating up in the water. They're not evaporating. And as this occurs, your system is going to start being exposed to adverse effects, namely scale buildup, corrosion, and bacteria. And the status quo way to address these issues is what you see in the top right corner of this slide, a chemical feed station. We're dosing the system with chemicals to protect the equipment from those increased mineral concentrations. The problem this presents is the chemicals are only able to protect your system up to a certain mineral concentration. When it becomes too dense and too saturated, your system is going to start being at risk of scale corrosion and bacteria. When we hit that point and that threshold of mineral concentration to protect your system, you initiate what's known as the blowdown process. When we open a valve, dump some of that concentrated tower water to the drain, and replenish with lower concentrated fresh makeup water. This starts getting into the first of the equations to determine the water efficiency of a cooling tower. The first being your makeup water is equal to your evaporation plus your blowdown. Everything that enters your cooling tower, your makeup, is equal to everything that leaves the cooling tower, your evaporation plus your blowdown. And there's an industry term that we're going to get into on this next slide called cycles of concentration. In its crudest form, your cycles of concentration is how many times am I reusing that drop of water in my cooling tower before it becomes too concentrated and I need to open that blowdown valve and send it to the drain. You can see on the left side of this slide a graph that represents your water volumes on your y-axis and your cycles of concentration on your x-axis. Think back to the equation I started with on the last slide. Your makeup is equal to your evaporation plus blowdown. That's what we're representing at each one of these levels of cycles on this graph. Green is your evaporation, red is your blowdown, blue is your total makeup. You'll notice that the green bar is constant throughout. That's our heat load, that's our evaporation load. That is completely independent of your cycles of concentration. What is dependent on your cycles of concentration is your blowdown, which is the red bar. Now, system of equations we like to refer to on the right side of this slide. The first we already talked about, your makeup is equal to your evaporation plus your blowdown, but the other two is where we start getting into cycles of concentration and relating those variables. Your cycles you can calculate a number of ways, one of which taking your makeup volume and dividing it by your blowdown volume, or what I find to be the easiest to communicate is your blowdown is your inverse of your cycles of concentration. So let's start on the left side of this graph for an example. Let's say we're at 2 cycles of concentration, or 1/2, 50% blowdown. That means 50% of the water is going to the drain and the other 50% is getting evaporated. So if there was a way we could go from 2 cycles to 25 cycles, or 1/25, 4% blowdown at that same evaporative load, that would be just under 50% opportunity for water savings.
As you can see, we calculate the amount of water going to the drain by taking the inverse of our cycles of concentration. So you can see that one of our biggest levers in being able to reduce the amount of water consumed in your cooling system is by moving to the right on this chart, by increasing our cycles of concentration and reducing our red bar on this chart, or reducing our blowdown. So that's our first and most important lever for water consumption savings. The second is to use an alternative water source that's either free or going to the drain. So that's using reclaimed or rainwater or groundwater, RO concentrate, DI discharge. That's our other lever to be able to save water at your site. All right, so how do we determine how many cycles of concentration we can run in your system? Well, the way that we do it with a chemical water treatment program is we use a term called Langelier Saturation Index, or LSI. LSI allows us to figure out at which maximum cycles of concentration we will be protected from scale corrosion and bacteria, and our chemical half-life will be effective. If we're running the high cycle program or the hybrid program at your site, our cycles of concentration are limited by different factors, and we'll talk about that in a later session.